Hello and welcome to our video on RobotBT, our behavior tree-based test case specification library for the robot framework. We present RobotBT on the International Symposium on Software Testing and Analysis in 2023 and demonstrate it in a live demonstration in this video. RobotBT allows the specification of robot test cases using behavior trees and thereby simplifies the specification and especially the readability complicated robot test cases by the use of behavior trees. At execution, RobotBT test cases behave like robot test cases, and they can be dynamically combined with standard robot test case specifications. In this video, we first motivate the need for easier readable specifications of complicated robot test cases and give an introduction to behavior trees on a real-world example. Finally, we demonstrate the specification of robot framework test cases using RobotBT in a live demonstration of our tool and conclude with the execution of the RobotBT test cases and a comparison to the standard robot test case execution. Our real-world example that we'll use in this talk, but also in our paper on ISTA, is taken from the GData Cyber Defense AG, a common provider of antivirus software and that uses robot test cases for testing their antivirus software's UI. Robot itself provides an abstraction for the test case specification and abstracts the code of the test case specification towards natural language by using so-called keywords, which are in the end functions, but are easier readable and less complicated to use than standard high-level programming languages. This makes it well suited for the implementation of simple test cases, also by non-programmers. However, when we look at practice, especially at GData, we notice that robot test cases quickly get unreadable, and GData had to come up with a lot of workarounds where they implemented a lot of logic in high-level programming languages such as Python or Java to avoid having the complexity in the robot test cases. On the right-hand side of the slide, you can see some excerpt of some test case from GData. So in this case, it's the specification of the so-called keyword, which is a reusable functionality that can be called from robot code. And what it does is it searches for the icon of the GData Cyber Defense antivirus software on the Windows system tray. Therefore, it behaves coarsely as follows. So first, it searches the visible icons on the Windows system tray. If it's found, everything is fine. If not, it continues to search for the grouping icon of Windows. If this is found, it opens the groups and search for the GData's antivirus software icon in this group. And if it's also not found there, it fails. This is now the robot code that consists out of the keywords that I already mentioned, but it also allows the use of variables. So just have a brief look at line 1 to give you a feeling on how robot works. In this line 1, we have a variable into which we want to store the result of a keyword execution. The keyword we'll now look at is the run and return status keyword that we call. Everything else in the line is now handed over to this keyword call as parameters, and the implementation of the keyword decides on how to handle this. In this case, run and return status executes the keyword, which is given next on this parameter list. In this case, wait until it succeeds, and run and return status takes no additional input, which means that everything else on this line will be passed as parameters to the wait until it succeeds keyword that is executed by run and return status. The status of the execution is then returned and stored in the variable. Wait until it succeeds itself is another keyword that takes additional parameters, in this case a number of 10 times, so it executes something 10 times and waits 100 milliseconds in between every execution. The third parameter now here is the element should exist, which is another keyword that is executed repeatedly by wait until it succeeds, and this takes a pointer to a location as its parameter, So it checks at the system icon of the GData cyber defense antivirus software exists at the given location, wait until it succeeds, executes this keyword now 10 times, waits in between the executions for 100 milliseconds, and stops for the first successful execution. And then the run and return status is some high-level implementation again of GData cyber defense that makes this line simpler than having to implement this logic of storing things into a variable using standard robot code, or maybe it's not even possible. So this way, robot still allows a more human-readable specification of test cases than this would be possible, for example, in Python. So people that want to write robot code need to know less programming details or knowledge. But still, if we already look at here this case, it's relatively complicated. And we only have if conditions and some nested keyword calls. Now imagine we would also have loops, and then it quickly gets unreadable. And that's a big issue because, in robot, we want to lift test case specification towards people that do, for example, requirements engineering to get test immediately against requirements, and also non-programming stuff. So we need, some way how we can improve here. And behavior trees are one way that allows us to specify such behavior, like searching for an icon where we can have different conditions under which we have to look at different positions, for example. And in behavior trees, we encode the logic in a tree where the nodes represent control flow or actions to be executed, and edges represent the order of execution. So in this figure here, I have an example behavior tree that realizes the testing that I have shown to you on the previous slide as behavior tree. So we start with a fallback node, which just means we execute the child nodes until we have the first successful execution of a child node. If we have it, we return success, otherwise we fail. Now we look on the left, we have a sequence. So all child nodes have to succeed in this case. And that's exactly now the logic I've shown to you. So we start with, we have to find the icon somewhere on the Windows tray. We don't care where. So one position where we find it is successful. So the first thing we check is a sequence. It has to be on the system tray. And if we find it there, we have to store the location. If we didn't find it on the system tray or weren't able to store the location of the system tray, we continue with our next possibility, which is we have to get the group item, and then we can continue this logic. So as you can see, behavior trees allow a relatively easy specification of conditional behaviors, which makes them a popular alternative to state machines. The way how it does it abstracts control flow into these control flow nodes and allows good visualization. Further, it's easily extensible. We can just add additional nodes to our behavior tree to change or adjust the behavior to our current needs, which makes it easy for maintenance. And also it's robust and resilient at execution. So if one of those nodes fails, we have a logic that continues the execution. So for example, if for some reason this is icon on tray action we perform fails, and that's not because we don't find the icon, but due to some exception, for example, our sequence node knows how to proceed. In this case, it will fail. We'll go back to our fallback node and just continue with the next alternative. So this makes it very robust at execution. Now the question is, how can we use this for specifying robot test cases? I've shown you an intuitive example, but for integrating it into robot, we came up with some textual domain-specific language that uses behavior trees as robot keywords. So these fallback and sequence nodes, for example, are keywords that are provided by our RobotBT extension to robot framework. So it's a library. And a fallback node, for example, would be a keyword one should pass, and a sequence node would be a keyword all should pass. And then what should be executed is handled as these additional parameters. And we indicate the depth in the tree, so where we are at the tree, by the use of dashes. So let me show you a concrete example. So I have here now a RobotBT implementation of this behavior tree shown on the right that realizes the robot code I've shown you in the beginning. And in the end, it's really every node in this tree is represented by a keyword. So this fallback is we have this one thing in our behavior tree that as a child should pass. Then we have the all should pass on the next indentation level. We have here one dash that indicates it, and these 3 dots are needed in a robot to indicate that this line 2 belongs to line 1. So we could also just write everything in one line, but in the end, we also in our text want to have this visual structure according to this tree. And then we continue with our next node, which checks if the item is on the tray. And this is now implemented using standard robot code, using this wait until it succeeds, try 10 times with 100 milliseconds in between the tries, and use the element should exist. So that's the code we have already seen in the initial robot example, but here we use now this behavior tree logic for orchestrating the execution of this and having also this conditional executions. And as you can see, our example code gets much shorter and also more readable this way. So in what follows, we'll give you now a live demonstration of our tooling for specifying RobotBT test cases, so using behavior trees in our real tooling. And there we use the code excerpt that is already used by me on the previous slides as an example, and show you also some more details of this real-world test suite from GData Cyber Defense.
The test case has 3 steps to look for the GData icon. If it's group or not, it should find it and click on it, and after clicking it should be opened. The UI, the GData Security Center, should be opened, and then it should close the application, and that's it. The test case consists of mainly 2 keywords, which are abstracted keywords. Abstracted keywords means they consist of several keywords. The test case says open the GData Security Center by the tray and close the GData Security Center. And this is the GData Security Center tray icon. And if you click on it, the UI should appear, and after appearing, you should close the GDSC. So let's go further to definition of the keyword, how it's has been implemented, and here you can see an implementation of the keyword which says is the tray icon not grouped, which will check if it's there as an example here or not. So if it's here, it will say it's not grouped true, and it will directly open by clicking on here. And if it's grouped, which this variable should be as false, which will be the case as you see right now here, and it should open the overflow notification area, and it should click on it. And we can go further to the implementation of those keywords, which looks a bit hard and difficult to understand. And second one is the close if notification tray pops, which is basically proves if there is some blocking notification here in this area, which can block the GData icon. So if there is some notification from Windows or from our side, can be any detection or any notification updates or something, it should close it. And after checking if it's group or not, and after closing the blocking window, it should know where to begin with. So it will either open from here or open the notification overflow area and open the GDSC from here using this keyword. That's the test case all about, and we will be seeing right now the test case identical test case implemented using the behavior tree, which is this one. So let's go down to the road and compare the both implementation with the use of behavior tree and without using the behavior tree. So in the first level, depth level, you can see you can implement the behavior tree. You can translate the same keyword into a behavior tree version, which will look like this, which you cannot notice a very big difference, which looks same. Both are readable, both are good to understand, but as soon as go difficult, as soon as the logic gets difficult, you can see the benefit of both implementation. This is the robot framework traditional implementation, and this is the behavior tree implementation, which are 100% identical what they do, but this implementation or this concept needs less place. It's better readable. Even the syntax highlighting is not yet implemented. It looks simpler and easier to understand, which you can see the benefit of the behavior trees. And as well as the second keyword, which is the close if the notification tray pop-ups, which you can also see the both versions, the all without behavior tree and with behavior tree. So let's get deeper in understanding what they do. So we can check line by line what this keyword does. This keyword actually proves if the not group variable exists, which means does this test case already has executed, and do I have a memory about the grouping state? If I already have the grouping state memory, so it doesn't need to be executed further, and I can just return from this keyword and say the grouping status is already in the memory, and the status is saved in this variable. So this is simply what the first line does, and the same line which can be found right here, which is under one should pass keyword. This keyword is actually a behavior tree node, which is equivalent to fallback node or selector node, as you also can see the name here. So selector node or one should pass node demands that its children, it's given direct children, at least one of them should pass. If it's the case, this father node, this parent node, should be executed successfully. So in this case, it says one should pass, and it's the first level child is variable should exist, and if it's the case, the execution passed and it returns from the keyword as it's given here with these two lines. This is simply for reading. This can be also written just like this. The 3 points actually means the same line, but it's written on this new line. So let's get a bit further. For explaining what the other steps are doing, we can see here exists sys tray, run keyword and return status, wait keyword until succeed. As I already mentioned, this is one line keyword. It also can be written in a one line. And what it does, it proves for 10 times for 100 milliseconds, which is around 1 second long, if it can found the tray icon here outside of the group. If it's the case, which you can see here, it says it's true, and it sets the not grouped variable to true. It says it's not grouped, and it returns from the keyword after setting the not grouped as a global variable, which can be accessed from everywhere in the test switch. So the same implementation can be seen here. After the one should pass, we have implemented the second node, which is a behavior tree sequence node, and in this node we can see it has been implemented the same keyword, which can be seen here with wait until succeeds. If it's the case and if it's executed successfully, it will execute the second one because it's in sequence behavior tree node, and it will be executing this one by setting the not grouped as true and returning from keyword. And then, as I already said, it's the same, writing those in one line. And after that, if it's not the case, that means it should be proven if it's grouped or not. Because of that, it proves if it's outside, and if it's the case, it fails. If it's not the case, it fails. I mean, the system tray grouping is this item here. So it has proved if GData tray icon was outside, it wasn't the case, as when we have reached here. That means this item should be the grouping show hidden icons item should be there. If it's also not the case, if it's also not there, so it means sorry, I couldn't find the GData tray icon, and it can fail, which is also here the case. And I will not going further to this test case, which is to this keyword, I mean, which is only clicking on this item, grouping item, to open the grouping section. And after opening the grouping section, the notification overflow GD tray icon should appear. That means this icon should be there. If it's the case, you can set the not group as false, and you can close the grouping section with using this keyword and return from keyword. If it's also not the case, it will fail, which is also implemented identically here under the behavior trees. And that's how we have proved that both keywords are identical. Thank you for watching. In the second video, you will be seeing the both test cases and even the third one in execution. And the third test case is this middle one, which contains one test case which can be implemented differently because we have the behavior tree logic, and instead of saving a variable as a global variable and then checking it if it's grouped or not, it can simply fail or pass with given step which means in this step, instead of saving some variable, it can simply fail if it's not there, and we will know it's not outside the group, so we will assume that it's inside, and we will go further to this test case, which is the same test case but different implementation, which takes less time to be executed and takes less code. Now, time for execution. I will be executing the 3 test cases: the fast checkup test case, which is implemented without behavior tree, and the test case which is implemented with the use of behavior tree, but one keyword has newly implemented for this purpose, which contains less step than the other, and the last but not least, the last test case, which is identical to the first test case but only implemented within the behavior tree. So, time to execution. Time for execution. I will be executing first of all the traditional one, and it should start right now. As you see, it will check outside of the group if the GData tray icon is there. If it didn't find it, it will click on the grouping and check in it if it's there. So it found it and reopened the grouping to open the GData UI, and it found the UI, and here's the test case execution. It took around 18 seconds to be executed, and the log can be seen here. Like as you see, there is no use of behavior trees. And I will be executing the identical test case, which is implemented with the use of behavior tree, which should also take the same execution time, around 18 seconds, maybe 17, 16, or 19 seconds. It depends on the click times and UI initialization times. So, as you see, it was an identical test case and it took identical time. And there are some test cases which are implemented with the use of behavior trees. So, and last but not least, the middle test case, which is implemented with a newly implemented keyword with less step, which will take a couple seconds less than others. And here's the third test case in execution. That's it. And if we refresh the log data, as you see, it took less than the other both, and it also implements the same test case.
In this video, we have shown to you how you can use behavior trees to simplify the specification of your robot test cases. Our tool RobotBT provides a textual language for specifying robot test cases using behavior trees. We use this language to specify the test cases of GData Cyber Defense AG using behavior trees and serving 5 engineers of them concerning the readability of the newly specified test cases using behavior trees. All 5 engineers stated that the new test case specifications are much more easier readable than the existing ones not using behavior trees, and that RobotBT is perfectly applicable in the context of GData. Further, in this video, we have shown to you how to work with this textual language provided by RobotBT and how to specify RobotBT test cases using behavior trees. And finally, we have shown to you that the execution of the RobotBT test cases does not differ from the execution of standard robot test cases, which makes them perfectly applicable to deploy in your testing pipelines. I hope we raised your interest in our work and RobotBT. If so, please have a look at our tool paper in the ISTA 2023 proceedings and the tool's implementation at GitHub. I'll provide you with the links to both in the video description. Thank you for watching.